Imagine a place where the universe's most powerful forces collide, where the very fabric of space and time is stretched to its breaking point. This isn't the plot of a sci-fi movie. It's the reality of black holes, and they're causing one of the biggest headaches in physics today. General relativity says information that falls into a black hole is lost forever, while quantum mechanics insists that information can never be destroyed. So, what's really happening to data in the heart of a black hole? Stick around, because we're diving into the information paradox, where the rules of the universe seem to break down, and the answers might just change everything we know about reality. The enigma of black holes. Black holes, those cosmic enigmas, have long captivated the minds of scientists and enthusiasts alike. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. This intense gravity results from matter being compressed into an incredibly small space. At the heart of a black hole lies the singularity, a point of infinite density where the laws of physics, as we know them, break down. Surrounding the singularity is the event horizon, the point of no return. Once an object crosses this boundary, it is inexorably pulled towards the singularity. This is where things get interesting, and also where the information paradox begins to unfold. General relativity, Einstein's theory of gravity, describes black holes with remarkable precision. It predicts that the information about the physical state of objects falling into a black hole is lost forever. This is because the event horizon acts like a cosmic sensor, hiding the singularity and any information about the infalling matter. From this perspective, black holes are the ultimate information destroyers. However, this idea clashes with the principles of quantum mechanics, which govern the behavior of particles at the smallest scales. Quantum mechanics posits that information can never be truly destroyed. It can be transformed or hidden, but it always remains accessible in some form. This fundamental conflict between two of the most successful theories in physics has given rise to the information paradox. The paradox deepens when considering the concept of black hole evaporation. In the 1970s, physicist Stephen Hawking proposed that black holes can emit radiation, a phenomenon now known as Hawking radiation. Over time, this radiation causes the black hole to lose mass and eventually evaporate completely. If the black hole disappears, where does the information about the matter that fell into it go? According to general relativity, it's gone forever, but quantum mechanics insists that information must be conserved. This apparent contradiction has sparked intense debate and speculation among physicists. Some theories suggest that the information is somehow encoded in the Hawking radiation, while others propose more exotic scenarios, such as the formation of white holes or the existence of hidden dimensions. One of the most intriguing aspects of the information paradox is the role of entropy. Entropy is a measure of the disorder or randomness in a system. In the context of black holes, it's closely related to the concept of information. The more information a black hole contains, the higher its entropy. However, as a black hole evaporates, its entropy decreases. This seems to violate the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease. Resolving this paradox requires a deeper understanding of the interplay between gravity, quantum mechanics, and thermodynamics. It's a challenge that continues to push the boundaries of our knowledge and fuel the quest for a unified theory of everything. Data, the invisible currency. In the vast expanse of the cosmos, data is the invisible currency that fuels our understanding of the universe. It's the language of reality, encoded in the fabric of space-time. Black holes, those enigmatic cosmic entities, pose a profound challenge to our grasp of this currency. They warp space-time so severely that nothing, not even light, can escape their grasp. This raises a fundamental question: what happens to the data, the information, that ventures too close to a black hole? General relativity, Einstein's masterpiece, describes gravity as the curvature of space-time caused by mass and energy. In this framework, a black hole's event horizon is a point of no return. Once information crosses this boundary, it's seemingly lost to the rest of the universe. This is the heart of the information paradox. If data is indeed the invisible currency of the cosmos, then black holes appear to be the ultimate banks, where deposits are made but withdrawals are impossible. This idea is deeply unsettling. as it suggests that the universe might not be deterministic, that the past might not entirely determine the future. Quantum mechanics, the theory governing the microscopic world, paints a different picture. It posits that information can never be truly lost. Every quantum state evolves in a predictable manner, and information is always conserved. This principle is so fundamental that it's often elevated to the status of a law. If quantum mechanics is correct, then the information that falls into a black hole must somehow escape, perhaps in a modified form. Some theories suggest that black holes might evaporate over time, slowly leaking information back into the universe. Others propose that the information is encoded on the event horizon itself, a concept known as the holographic principle. The conflict between these two theories is a hot topic in theoretical physics. It's a battle between the cosmic bank of general relativity, where information deposits are irreversible, and the quantum ledger, where every entry is preserved. Resolving this paradox could require a theory of quantum gravity, a framework that seamlessly merges general relativity and quantum mechanics. Until then, the information paradox remains one of the most intriguing puzzles in modern physics. It's a reminder that even in the age of information, the universe still holds secrets. The information paradox unveiled. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and intense study. At the heart of this intrigue lies the information paradox, a conundrum that arises when trying to reconcile two fundamental theories of physics: general relativity and quantum mechanics. General relativity, Einstein's brainchild, suggests that black holes are extraordinarily simple objects. They can be completely described by just three parameters: mass, charge, and angular momentum. When something falls into a black hole, according to this theory, all information about its internal state is lost forever. This is often referred to as the no-hair theorem. It implies that a black hole's event horizon is an indelible barrier beyond which information cannot escape. Quantum mechanics, on the other hand, paints a different picture. This theory posits that information can never be truly lost. It's a fundamental principle, often encapsulated in the phrase, "information is conserved." In the quantum world, every particle and its properties are encoded with information. When these particles interact, the information is preserved, even if the particles themselves are transformed. This principle has been extensively tested and confirmed in countless experiments. The clash between these two theories is profound. If general relativity is correct, information can be lost in a black hole. But if quantum mechanics is right, it cannot. This is the essence of the information paradox. The paradox becomes even more intriguing when considering the concept of black hole evaporation. In the 1970s, physicist Stephen Hawking theorized that black holes can emit radiation, a process now known as Hawking radiation. Over time, this radiation causes the black hole to lose mass and eventually evaporate completely. If this happens, where does the information about the black hole's contents go? Does it disappear, violating quantum mechanics? Or is it somehow preserved, challenging general relativity? These questions remain unanswered, fueling ongoing research and debate. One proposed solution to the paradox is the idea of black hole complementarity. This theory suggests that information is both destroyed and preserved, but in a way that prevents any paradoxical consequences. According to this view, an observer falling into a black hole would see the information preserved inside the event horizon. Meanwhile, an outside observer would see the information preserved in the Hawking radiation. However, this theory is not without its critics and unresolved issues. Another intriguing possibility is the holographic principle, which posits that all the information contained within a volume of space can be encoded on the boundary of that space. In the context of a black hole, this would mean that the information is not lost, but is instead encoded on the event horizon. These ideas are still speculative and require more rigorous theoretical and experimental exploration. Black holes, cosmic information vaults? Black holes, those enigmatic cosmic entities, have long been a subject of fascination and study. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. This intense gravity is a result of matter being compressed into an incredibly small space. At the heart of a black hole lies the singularity, a point of infinite density where the laws of physics, as we know them, break down. Surrounding the singularity is the event horizon, a boundary beyond which all matter and energy are inexorably drawn in. This boundary marks the point of no return, a one-way ticket into the unknown. The concept of black holes as cosmic information vaults is intriguing. According to general relativity, the information about the physical state of objects that fall into a black hole is lost forever. This is because the black hole's event horizon acts like a cosmic sensor, hiding the details of the infalling matter from the outside universe. However, this idea clashes with the principles of quantum mechanics, which state that information can never be truly destroyed. This conflict gives rise to the information paradox, a puzzle that has baffled physicists for decades. Quantum mechanics suggests that information must be conserved, meaning that the details of the particles that fall into a black hole should somehow be preserved. One proposed solution to the paradox is the idea of black hole radiation, or Hawking radiation. This theoretical process suggests that black holes can emit particles, slowly losing mass and eventually evaporating. If this is true, the information contained within the black hole might be released back into the universe as the black hole disappears. However, this raises another question. How is the information encoded in the radiation? The exact mechanism remains unclear, and the debate continues. Another perspective comes from the holographic principle, which posits that the information contained within a volume of space can be encoded on the boundary of that space. Applied to black holes, this principle suggests that the information about the matter that falls in is somehow encoded on the event horizon. This idea is still speculative, but it offers a potential way to reconcile the conflicting views of general relativity and quantum mechanics. The information paradox remains one of the most profound and challenging questions in modern physics, driving researchers to explore the deepest mysteries of the universe. The second law of thermodynamics, a challenge. The second law of thermodynamics is a fundamental principle that states the total entropy, or disorder, of an isolated system can only increase over time. This law has profound implications for our understanding of black holes and the information paradox. When matter falls into a black hole, it appears to cause a decrease in the total entropy of the universe, which seems to violate the second law. This is because the information about the matter's state is lost behind the event horizon, making it impossible to determine its original entropy. However, black holes themselves have an entropy given by the Bekenstein-Hawking formula, which is proportional to the area of their event horizon. This suggests that the information might not be lost, but is instead encoded on the black hole's surface. Yet, this raises another question. How is this information stored and retrieved? General relativity and quantum mechanics offer conflicting views on this matter. According to general relativity, information that crosses the event horizon is lost forever. This is because the gravitational pull is so strong that not even light can escape, making the interior of a black hole inaccessible from the outside universe. This perspective supports the idea that the second law is violated, as the entropy of the matter is seemingly lost. On the other hand, quantum mechanics principles, such as unitarity, suggest that information can never be truly lost. This is because quantum states evolve in a reversible manner, meaning that the information about a system's initial state should, in theory, be recoverable. This conflict between the two theories has led to intense debate and research, with no consensus yet reached. One proposed solution to this challenge is the idea of black hole radiation, put forward by Stephen Hawking. He suggested that black holes can emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, would cause the black hole to slowly lose mass and eventually evaporate. If this is the case, the information about the matter that fell into the black hole might be released back into the universe during this process. However, this raises another issue. The information is released in a seemingly random and thermal manner, making it difficult to see how the original information can be recovered. This has led to the information paradox, a deep and unresolved question in theoretical physics. The information paradox is not just a theoretical curiosity. It has significant implications for our understanding of the universe. If information is truly lost in black holes, it would mean that the second law of thermodynamics is violated, which would have profound consequences for our understanding of entropy and the arrow of time. On the other hand, if information is preserved, it would require a radical revision of our understanding of black holes and general relativity. This challenge has sparked a wealth of research and debate, with physicists exploring ideas such as firewall paradoxes, black hole complementarity, and even the holographic principle. Each of these ideas offers a different perspective on how information might be preserved, but none have yet been proven or widely accepted. The information paradox remains one of the most pressing and fascinating challenges in modern physics. Hawking radiation, a glimpse of escape, black holes, those enigmatic cosmic entities, have long been a subject of fascination and perplexity. They warp space-time so severely that nothing, not even light, can escape their grasp. Yet, in the 1970s, physicist Stephen Hawking proposed a mind-bending idea. Black holes might not be entirely black. He suggested that they could emit a type of radiation, now known as Hawking radiation, which could potentially allow information to escape. This idea has significant implications for the information paradox, a conundrum that arises from the conflicting predictions of general relativity and quantum mechanics. General relativity, Einstein's theory of gravity, dictates that the information about the physical state of objects falling into a black hole is lost forever. This is because black holes are characterized by only three parameters: mass, charge, and angular momentum. Once an object crosses the event horizon, it's game over for its unique information. However, quantum mechanics, the theory governing the microscopic world, posits that information can never be truly lost. This is a fundamental principle, and its violation would imply that the universe doesn't follow any rules at all. So where does the truth lie? It's a tough question, and Hawking radiation might hold a clue. Hawking radiation is a quantum effect that occurs near the event horizon. According to quantum field theory, the vacuum of space is not truly empty, but filled with virtual particles popping in and out of existence. Near the event horizon, one of these virtual particles can be pulled into the black hole, leaving its partner to escape as Hawking radiation. This process causes the black hole to lose mass and eventually evaporate. Over time, the black hole would disappear, taking any information it had swallowed with it. But here's the twist. The information carried by the infalling particle and the Hawking radiation seems to be different. This suggests that information might not be preserved, which is a problem for quantum mechanics. However, the story doesn't end there. Some physicists argue that the information isn't lost, but is instead encoded in the Hawking radiation in a highly complex way. This idea, known as the black hole complementarity, suggests that the information is both inside the black hole and outside in the radiation, but it can't be observed in both places at the same time. It's a bit like the observer effect in quantum mechanics, where measuring a system disturbs it. But this interpretation is not without its critics. Others propose that the information is somehow preserved in the black hole's entropy, a measure of its disorder. Yet, the exact mechanism remains elusive. The information paradox is far from resolved, and Hawking radiation, with its tantalizing glimpse of escape, continues to fuel the debate. The no-hair theorem, stripping down information. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and intense study. At the heart of this intrigue lies the information paradox, a conundrum that arises from the conflicting predictions of general relativity and quantum mechanics. General relativity, Einstein's theory of gravity, suggests that information about the physical properties of objects falling into a black hole is lost forever, while quantum mechanics, the theory governing the behavior of particles at the atomic and subatomic scale, posits that information can never be truly destroyed. This tension between the two fundamental theories has sparked decades of debate and research. The no-hair theorem, a consequence of general relativity, plays a pivotal role in this paradox. Proposed by John Wheeler, the theorem states that a black hole can be completely described by only three properties: its mass, electric charge, and angular momentum. This means that any other information about the matter that formed the black hole, such as its chemical composition or magnetic field, is irretrievably lost. This idea is often summarized by the phrase, "black holes have no hair," implying that they are devoid of any additional distinguishing features. The theorem suggests that as matter falls into a black hole, it is stripped down to these bare essentials, leaving behind no trace of its original identity. However, this stark prediction clashes with the principles of quantum mechanics. Quantum theory insists on the conservation of information, asserting that the state of a physical system at one time should determine its state at any other time. If information is lost when matter falls into a black hole, this would violate the fundamental tenets of quantum mechanics. This conflict has led to a plethora of theoretical explorations, including the idea of black hole radiation proposed by Stephen Hawking. Hawking's work suggested that black holes can emit radiation, causing them to slowly evaporate over time. This process, now known as Hawking radiation, implies that information might be gradually leaked back into the universe, although the exact mechanism remains unclear. The information paradox remains one of the most profound and unresolved questions in modern physics. It challenges our understanding of the fundamental laws of nature and the interplay between gravity and quantum mechanics. Various theories have been proposed to resolve the paradox, including the holographic principle, which suggests that the information inside a black hole might be encoded on its event horizon, and the idea of black hole complementarity, which posits that information is preserved in a way that is consistent with both general relativity and quantum mechanics. Despite these efforts, the paradox endures, serving as a testament to the depths of our ignorance and the vastness of the mysteries that the universe holds. The holographic principle, a cosmic hard drive? Black holes, those enigmatic cosmic entities, have long puzzled scientists with their insatiable appetite for information. According to general relativity, anything that crosses a black hole's event horizon is lost to the universe forever. This includes information about the physical state of objects, their composition, and their history. This idea gives rise to the information paradox, a conflict between general relativity and quantum mechanics, which posits that information can never be truly destroyed. The paradox is a hotly debated topic, with no consensus in sight. Enter the holographic principle, a mind-bending concept that might just offer a way out of this conundrum. Proposed by theoretical physicist Gerard T. Hooft and later expanded by Leonard Susskind, the principle suggests that all the information contained within a volume of space can be encoded on the boundary of that space. Think of it like a cosmic hard drive, where the universe's data is stored on a lower dimensional surface. This idea is inspired by the mathematics of string theory and black hole thermodynamics. In the context of black holes, the holographic principle implies that the information swallowed by a black hole isn't lost forever. Instead, it's encoded on the event horizon, the boundary marking the point of no return. This encoding is incredibly efficient, with each Planck area, the smallest unit of area in nature, storing a single bit of information. For a black hole the mass of the Sun, this would amount to an astonishing 10^71 bits of information. This idea is still speculative, but it's a tantalizing possibility that could help resolve the information paradox. The holographic principle also has implications for our understanding of the universe itself. Some interpretations suggest that our 3D universe might be a projection from a 2D surface, much like a hologram. This idea is still in its infancy, but it's a fascinating avenue of research that could revolutionize our understanding of reality. It's important to note that the holographic principle is not a proven theory, but a powerful tool for exploring the deepest mysteries of the cosmos. It's a testament to the incredible creativity and ingenuity of human thought, pushing the boundaries of our understanding and challenging our perceptions of reality. Unitarity, the conservation of information. In the vast expanse of the cosmos, black holes stand as enigmatic entities, their nature shrouded in mystery. At the heart of this mystery lies the information paradox, a conundrum that arises from the conflicting predictions of general relativity and quantum mechanics. General relativity, Einstein's theory of gravity, suggests that information about the physical state of objects falling into a black hole is lost forever. This is because black holes are characterized by only three parameters: mass, charge, and angular momentum. Once an object crosses the event horizon, it's gone, and all information about it is seemingly erased. This is often referred to as the no-hair theorem, implying that black holes have no other distinguishing features or hair. Quantum mechanics, however, paints a different picture. It posits that information can never be truly lost, only transformed. This principle is known as unitarity, the conservation of information. In other words, the total amount of information in the universe remains constant. If you start with a quantum system in a certain state, and it evolves over time, the total information about that system is preserved. This is a fundamental tenet of quantum mechanics and has been confirmed by countless experiments. The paradox arises when we try to reconcile these two theories. If information is indeed lost in a black hole, as general relativity suggests, then quantum mechanics would be violated. But if information is conserved, as quantum mechanics dictates, then general relativity must be incomplete or incorrect. The unitarity of quantum mechanics implies that the information about the objects that fall into a black hole must somehow be encoded in the black hole itself. One popular idea is that the information is stored on the event horizon, the boundary of the black hole. This is often referred to as the holographic principle, which suggests that the information in a volume of space can be encoded on the boundary of that space. However, this idea is still highly speculative and lacks experimental evidence. Another possibility is that the information is somehow radiated back out into the universe through a process known as Hawking radiation. This is a type of radiation that is predicted to be emitted by black holes due to quantum effects near the event horizon. However, this radiation is incredibly faint and would take an incredibly long time to carry away all the information that fell into the black hole. The information paradox remains one of the most pressing questions in theoretical physics. It's a topic of intense debate and research, with physicists proposing a wide range of ideas and theories to resolve it. Some physicists argue that the paradox is a sign that our current understanding of gravity and quantum mechanics is incomplete. They believe that a theory of quantum gravity, which would unify these two fundamental theories, would provide a resolution to the paradox. Others argue that the paradox is a result of our incorrect interpretation of the laws of physics. They believe that a better understanding of the nature of information and its role in the universe would provide a resolution. Regardless of the outcome, the information paradox continues to push the boundaries of our understanding of the universe and the laws that govern it. The black hole information paradox, a closer look. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and intense study. They warp space-time to such an extent that nothing, not even light, can escape their grasp once it crosses the event horizon. This is a well-established consequence of general relativity, Einstein's theory of gravity. However, when it comes to the information contained within the matter that falls into a black hole, things get murky. This is where the black hole information paradox comes into play. General relativity suggests that the information about the physical state of objects that fall into a black hole is lost forever. This is because the black hole's event horizon acts like a cosmic censorship, hiding the interior from the outside universe. Over time, black holes evaporate through a process called Hawking radiation, a quantum mechanical effect predicted by Stephen Hawking. As the black hole loses mass through this process, it eventually disappears completely. If the information about the infalling matter is indeed lost, this would violate a fundamental principle of quantum mechanics, the conservation of information. This principle states that information about a physical system can never be completely erased. Quantum mechanics, on the other hand, posits that information can never be truly destroyed. It can be transformed or encoded in different ways, but it can't just vanish into thin air. This leads to a direct conflict with the predictions of general relativity. If information is indeed preserved, then it must be somehow encoded in the Hawking radiation emitted by the black hole. However, the exact mechanism by which this happens remains unknown. This is the crux of the black hole information paradox, a clash between two of our most successful physical theories. Several theoretical approaches have been proposed to resolve this paradox. One idea is that the information is somehow encoded in the subtle correlations between the particles of Hawking radiation. This is often referred to as the holographic principle, which suggests that the information about a volume of space can be encoded on its boundary. Another proposal involves the idea of black hole remnants, hypothetical objects that would form once a black hole has evaporated completely, preserving the information. Yet another approach is the fuzzball model, which suggests that black holes are not the smooth, featureless objects predicted by general relativity, but rather chaotic, quantum objects with no event horizon. Each of these ideas has its own set of problems and unanswered questions, highlighting the complexity of the paradox. Quantum mechanics versus general relativity. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and study. They warp space-time to such an extent that nothing, not even light, can escape their grasp. This is where general relativity, Einstein's theory of gravity, reigns supreme. It describes how massive objects like black holes curve space-time, creating the intense gravitational fields that characterize these celestial bodies. According to general relativity, any information about the physical state of objects that fall into a black hole is lost forever. This is known as the no-hair theorem, which states that a black hole has only three independent physical properties: mass, charge, and angular momentum. All other information about the matter that formed the black hole or falls into it is irretrievably lost. Quantum mechanics, on the other hand, paints a vastly different picture. It governs the behavior of particles at the smallest scales and is founded on the principle of unitarity. This principle asserts that the probability of all possible outcomes of a quantum mechanical system must sum to 1. In other words, information can never be lost. It can only be transformed or transmitted. When applied to black holes, quantum mechanics suggests that information about the state of particles that fall in should somehow be preserved and eventually re-emitted. This leads to a profound conflict with general relativity, which insists that information is lost forever within a black hole. The clash between these two fundamental theories gives rise to the information paradox. At the heart of this paradox lies a deep question: what happens to the information of particles that fall into a black hole? General relativity suggests it is lost, while quantum mechanics insists it must be preserved. This contradiction has puzzled physicists for decades. One of the most prominent attempts to resolve the paradox is the idea of black hole radiation proposed by Stephen Hawking. According to this theory, black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. Over time, the black hole loses mass and eventually evaporates completely. However, this process raises another question. If the black hole evaporates, where does the information go? Hawking radiation seems to carry away only a scrambled version of the original information, leaving the paradox unresolved. Efforts to reconcile these two theories have led to the development of various hypotheses and models. One such model is the holographic principle, which suggests that the information within a volume of space can be encoded on a lower dimensional boundary, such as the event horizon of a black hole. This idea draws inspiration from string theory, which posits that fundamental particles are not zero-dimensional points, but rather one-dimensional strings that vibrate at different frequencies. String theory attempts to unify quantum mechanics and general relativity by providing a framework where both theories emerge as different aspects of a more fundamental theory. However, despite these advances, the information paradox remains one of the most challenging problems in theoretical physics. It continues to drive research and debate, pushing the boundaries of our understanding of the universe. The Firewall Paradox, a burn notice. Black holes, those enigmatic cosmic entities, have long been a hotbed for theoretical physics debates. At the heart of these discussions lies the information paradox, a conundrum that arises when trying to reconcile general relativity with quantum mechanics. The former suggests that anything that crosses the event horizon of a black hole is lost to the universe forever, while the latter insists that information can never truly be destroyed. This clash of titans sets the stage for the Firewall Paradox, a particularly fiery twist in this ongoing saga. Picture a black hole, a region of space where the gravitational pull is so strong that not even light can escape. According to general relativity, an object falling into a black hole would be stretched and squished into a stream of particles, a process aptly named spaghettification. Once past the event horizon, this object would be hidden from the outside universe, its information seemingly lost forever. This is the essence of the information paradox. Quantum mechanics, however, states that information can never be completely erased. This leads to a contradiction, a paradox that has left physicists scratching their heads. Enter the Firewall Paradox, a theoretical scenario proposed by a group of physicists in 2012. They suggested that the information isn't lost, but is instead preserved in a highly energetic region just inside the event horizon, a sort of wall of fire. This firewall would incinerate anything that tries to pass through, preserving information by preventing it from being lost in the singularity. The idea is controversial, to say the least. It challenges the equivalence principle, a cornerstone of general relativity that states that the effects of a uniform gravitational field are indistinguishable from those of constant acceleration. In other words, if you're in a closed box, you can't tell if you're standing on a planet or accelerating through space. The Firewall Paradox suggests that this principle might not hold at the event horizon, a radical idea that has sparked intense debate. The Firewall Paradox is a stark reminder of how much we still don't understand about black holes and the fundamental laws of the universe. It's a puzzle that encapsulates the tension between two of our most successful theories, a tension that physicists are eager to resolve. Some propose that the firewall is a red herring, a misstep in our understanding of quantum mechanics. Others argue that it's a sign that we need to rethink our approach to general relativity. Regardless, the Firewall Paradox is a fascinating example of how science progresses, not in leaps and bounds, but in a series of steps, stumbles, and occasional backtracks. It's a testament to the complexity of the universe and the enduring mystery of black holes. Complementarity, a dance of perspectives. Black holes, those cosmic enigmas, have long been the stage for a thrilling scientific drama. At the heart of this play is the information paradox, a conundrum that pits two of our most trusted physical theories against each other, general relativity and quantum mechanics. The paradox arises when we consider what happens to data, or information, as it falls into a black hole. General relativity, Einstein's brainchild, suggests that information is lost forever, swallowed by the black hole's insatiable maw. Quantum mechanics, however, insists that information can never be truly destroyed. It's a standoff that has physicists scratching their heads and reaching for their chalkboards. Enter complementarity, a principle that might just offer a way out of this impasse. It's not a solution per se, but rather a dance of perspectives, a way of looking at the problem from different angles. In the context of black holes, complementarity suggests that both general relativity and quantum mechanics are correct, but they're describing different aspects of the same reality. It's like watching a magic trick from two different vantage points. From one angle, you see the magician make a dove appear out of thin air. From another, you see the assistant pass the dove to the magician. Both perspectives are true, but they tell different parts of the story. One of the most compelling examples of this dance is the black hole information paradox itself. From the perspective of an outside observer, general relativity says that information is lost as it crosses the event horizon. But from the perspective of an infalling observer, quantum mechanics says that information is preserved, encoded in some way on the black hole's event horizon. Both perspectives are valid, but they seem to contradict each other. This is where the dance becomes a tango, a complex interplay of viewpoints that challenges our understanding of reality. Complementarity doesn't provide a definitive answer to the information paradox. Instead, it offers a framework for understanding why the paradox exists in the first place. It's a reminder that our universe is complex and multifaceted, and that sometimes the truth lies not in choosing one perspective over another, but in embracing them both. So, the next time you find yourself staring up at the night sky, wondering about the mysteries of black holes, remember, the dance of perspectives is far from over. ER equals EPR, a wormhole connection? Black holes have long been a source of fascination and perplexity in the world of physics. They warp space-time so severely that nothing, not even light, can escape their grasp. Yet, they also pose a profound puzzle known as the information paradox. At its core, the paradox questions what happens to the information about the physical state of objects that are swallowed by a black hole. According to quantum mechanics, information must be conserved, meaning it cannot be destroyed. However, general relativity suggests that information about the state of matter inside a black hole is lost forever once it crosses the event horizon. This conflict between two fundamental theories has left physicists scratching their heads for decades. Enter the ER equals EPR conjecture, a bold idea proposed by physicists Juan Meldacena and Leonard Susskind. The name is a nod to two sets of initials, ER, standing for Einstein and Rosen, who first theorized the existence of wormholes, Einstein-Rosen bridges, and EPR, referring to Einstein, Podolsky, and Rosen, who formulated the EPR paradox, a thought experiment that challenged the completeness of quantum mechanics. The conjecture suggests a deep, unexpected connection between these two seemingly unrelated concepts. Specifically, it posits that the entanglement of two particles, a quantum phenomenon where particles become intrinsically linked and the state of one instantly influences the other, might be equivalent to a wormhole connecting two points in spacetime. This is a radical idea, blending the strange world of quantum mechanics with the mind-bending nature of general relativity. The ER equals EPR conjecture offers a potential pathway to resolving the information paradox. If entangled particles are indeed connected by wormholes, then the information about the state of matter falling into a black hole might not be lost after all. Instead, it could be encoded in the entangled particles that escape the black hole's grasp. This would mean that the information is preserved, aligning with the principles of quantum mechanics. Moreover, it could provide a way to reconcile general relativity and quantum mechanics, two pillars of modern physics that have stubbornly resisted unification. The idea is still speculative, and much work remains to be done to test its validity. Yet, it represents a tantalizing glimpse into the profound connections that may underlie the fabric of the universe. The implications of the ER equals EPR conjecture are vast and far-reaching. If proven true, it could revolutionize our understanding of black holes, quantum mechanics, and the nature of space-time itself. It might also pave the way for new technologies, such as quantum computers that exploit the entanglement wormhole connection for unprecedented processing power. However, the conjecture is not without its critics. Some physicists argue that the evidence supporting the idea is still too tenuous, and more rigorous theoretical and experimental work is needed. Others point out that the conjecture raises as many questions as it answers, such as how exactly the entanglement wormhole connection works and what its implications are for the structure of space-time. Despite these challenges, the ER equals EPR conjecture remains a vibrant and active area of research, offering a tantalizing glimpse into the deep and mysterious workings of the universe. The Page Curve, a tale of two states. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and debate among physicists. At the heart of this intrigue lies the information paradox, a conundrum that arises from the conflicting predictions of general relativity and quantum mechanics. The paradox hinges on the fate of data, or information, that ventures too close to a black hole's event horizon. General relativity suggests that this information is lost forever, while quantum mechanics vehemently disagrees, insisting that information can never be truly destroyed. This clash of titans sets the stage for a captivating exploration of the Page Curve, a theoretical construct that attempts to reconcile these two states. The Page Curve, named after physicist Don Page, is a mathematical description of how information behaves as it interacts with a black hole. It posits that information can be in one of two states, entangled or disentangled. Entanglement is a quantum phenomenon where two particles become intrinsically linked, such that the state of one directly influences the state of the other, no matter the distance between them. When information falls into a black hole, it becomes entangled with the black hole's degrees of freedom, a state known as the early time behavior. This is the quantum mechanical perspective, where information is preserved but inaccessible. Meanwhile, general relativity paints a different picture. It suggests that as the black hole evaporates via Hawking radiation, information is gradually lost, a process described by the late-time behavior of the Page Curve. This is the classical perspective, where information is ultimately destroyed. The tension between these two states is what makes the Page Curve so intriguing. On one hand, you have the early time behavior, where information is preserved through entanglement. On the other, the late time behavior, where information is lost to the void. The Page Curve suggests that these two states are not mutually exclusive, but rather different phases of the same process. It proposes that as a black hole evaporates, it undergoes a phase transition, shifting from the early time behavior to the late time behavior. This transition is a hotly debated topic, with some physicists arguing that it violates the principles of quantum mechanics, while others believe it could be the key to resolving the information paradox. Recent advancements in theoretical physics, particularly in the field of quantum gravity, have shed new light on the Page curve. Researchers have proposed that the phase transition could be driven by quantum effects near the event horizon, where the intense gravitational field causes space-time itself to become quantum entangled. This would allow information to be preserved even as the black hole evaporates, effectively reconciling the two states described by the Page curve. However, these ideas are still speculative, and much work remains to be done before a definitive answer can be found. The information paradox, and the Page curve that attempts to resolve it, remain one of the most compelling and challenging problems in modern physics. Decoherence, the fading of information. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and debate among physicists. At the heart of this intrigue lies the information paradox, a conundrum that arises when trying to reconcile two fundamental theories of physics: general relativity and quantum mechanics. The paradox questions what happens to information about the physical state of objects that are consumed by black holes. Does it disappear forever, or is it somehow preserved? This is where the concept of decoherence comes into play, a process that blurs the line between quantum and classical physics. Decoherence is a quantum phenomenon where quantum systems interact with their environment, causing their quantum behavior to effectively disappear. In the context of black holes, it's often suggested that information about infalling matter might decohere, making it inaccessible to external observers. This fading of information is a hotly debated topic. Some physicists argue that decoherence could be the key to resolving the information paradox, while others remain skeptical. The idea is that even if information is not destroyed, it might become so scrambled and dispersed that it's practically lost. Think of it like trying to reconstruct a shredded document. The information is still there, but it's so mixed up that it's nearly impossible to retrieve. However, this interpretation isn't without its challenges. Quantum mechanics, with its principle of unitarity, suggests that information should never be lost. It's a fundamental tenet of the theory. On the other hand, general relativity, when applied to black holes, seems to imply that information can indeed be destroyed. This conflict between the two theories is what makes the information paradox so perplexing. Decoherence adds another layer to this puzzle. It's a complex process that's not fully understood, especially when it comes to extreme environments like black holes. Some researchers propose that decoherence could lead to a form of information leakage, where information slowly escapes the black hole's grasp. Others suggest that it might be a red herring, distracting from the real solution to the paradox. In the quest to understand the information paradox, physicists have explored various avenues. They've delved into the intricacies of quantum entanglement, the holographic principle, and even the nature of space-time itself. Each of these areas offers potential insights into what happens to information in black holes. Yet, despite these efforts, the paradox remains unsolved. Decoherence, with its role in the fading of information, is just one piece of this complex puzzle. It's a reminder of how much we still have to learn about the universe and the fundamental laws that govern it. The journey to unravel the information paradox is far from over, and it's a journey that continues to push the boundaries of our understanding. The role of entanglement, a quantum web. Quantum entanglement, a phenomenon Einstein famously referred to as spooky action at a distance, plays a pivotal role in the information paradox surrounding black holes. At its core, entanglement is a quantum mechanical process that links particles in such a way that the state of one can instantly affect the state of another, regardless of the distance separating them. This interconnectedness is not just a theoretical curiosity. It's a fundamental aspect of quantum mechanics that has been experimentally verified. When particles become entangled, they form a quantum web, a vast and intricate network of connections that underpins the behavior of quantum systems. This web is not static, it's dynamic and ever-changing, reflecting the probabilistic nature of quantum states. In the context of black holes, entanglement becomes a crucial player in the information paradox. According to general relativity, Information that crosses the event horizon of a black hole is lost forever, seemingly violating the principles of quantum mechanics, which dictate that information must be conserved. However, quantum mechanics introduces a twist. When particles near the event horizon become entangled, they create a quantum web that stretches across the horizon. This entanglement suggests that information might not be lost, but instead becomes encoded in the entangled particles. The paradox arises because general relativity and quantum mechanics offer conflicting views on what happens to this information. The role of entanglement in resolving the information paradox is still a topic of intense debate. Some theories propose that the entangled particles outside the black hole retain the information, effectively creating a quantum copy. Others suggest that the information is somehow scrambled and reemerges through a process known as Hawking radiation. This radiation, predicted by Stephen Hawking, consists of particles that escape from the black hole, potentially carrying information with them. The quantum web formed by entanglement could facilitate this information transfer, but the exact mechanism remains unclear. What is clear is that entanglement introduces a layer of complexity that challenges our understanding of black holes and the nature of information itself. The information paradox highlights the deep chasm between general relativity and quantum mechanics. While general relativity describes the large-scale structure of the universe, quantum mechanics governs the behavior of particles at the smallest scales. Entanglement, with its ability to link particles across vast distances, bridges these scales in a way that neither theory can fully explain on its own. This quantum web of entanglement suggests that information might not be lost but transformed, encoded in the intricate connections between particles. The paradox serves as a reminder of how much we still have to learn about the fundamental laws of the universe. It's a puzzle that continues to captivate physicists, driving them to explore the boundaries of our knowledge and push the limits of human understanding. The information paradox and the multiverse. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and perplexity. At the heart of this intrigue lies the information paradox, a conundrum that arises from the conflicting predictions of general relativity and quantum mechanics. General relativity, Einstein's theory of gravity, suggests that anything that crosses the event horizon of a black hole is inevitably pulled towards the singularity at its center, leading to a loss of information. This seems to violate a fundamental principle of quantum mechanics, which posits that information can never be truly lost. The paradox intensifies when considering the multiverse, a hypothetical set of possible universes, each with its own set of fields and interactions. In the multiverse, black holes could potentially serve as gateways to other universes. This idea, proposed by some physicists, suggests that information might not be lost but instead transferred to another universe. However, this is purely speculative, as there is no empirical evidence to support the existence of the multiverse or the transfer of information between universes. The concept of the multiverse itself is a contentious one, with some physicists arguing that it is a mathematical construct rather than a physical reality. Despite this, the idea persists, fueled by the desire to resolve the information paradox and reconcile the two pillars of modern physics. Another intriguing aspect of the information paradox and the multiverse is the concept of black hole complementarity. This idea, proposed by physicists like Leonard Susskind, suggests that information is not lost but is instead encoded on the event horizon of the black hole. From the perspective of an outside observer, the information appears to be lost, but from the perspective of an infalling observer, the information is preserved. This seems to resolve the paradox, but it raises new questions about the nature of reality and the role of the observer. The multiverse could potentially play a role in this scenario, with different versions of reality corresponding to different observers. The information paradox and the multiverse also have implications for the study of quantum gravity, the elusive theory that seeks to unify general relativity and quantum mechanics. Some physicists argue that the resolution of the information paradox could provide clues about the nature of quantum gravity. Others suggest that the multiverse could be a manifestation of quantum gravity, with each universe corresponding to a different quantum state. However, these ideas are highly speculative, and much more research is needed to understand the true nature of black holes. the multiverse, and the fundamental laws of the universe. Black holes as information sponges. Black holes, those cosmic enigmas with gravitational pulls so strong that not even light can escape, have long been a subject of fascination and study. They are often described as information sponges, a metaphor that captures their ability to absorb and hold onto vast amounts of data. This data isn't in the form of ones and zeros, but rather, it's the information that defines the particles and objects that fall into a black hole. This includes everything from the particles' quantum states to their positions and velocities. The concept of black holes as information sponges is central to the information paradox, a conflict between two of our most trusted theories in physics: general relativity and quantum mechanics. General relativity, Einstein's theory of gravity, suggests that the information about the particles that fall into a black hole is lost forever. When a particle falls into a black hole, it's pulled into the singularity at the center, where it's crushed out of existence. From this perspective, the information about that particle is gone, and there's no way to recover it. This idea is often illustrated with the concept of the event horizon, the point of no return around a black hole. Once something crosses this boundary, it's gone for good, taking its information with it. Quantum mechanics, on the other hand, has a different take. This theory, which governs the behavior of particles at the smallest scales, has a rule: information can never be truly lost. It can be scrambled, hidden, or transformed, but it can't be destroyed. This principle is known as unitarity, and it's a cornerstone of quantum mechanics. So, when a particle falls into a black hole, quantum mechanics says its information must be preserved somewhere. But where? This is where the idea of black holes as information sponges comes into play. Some theories suggest that the information is encoded on the event horizon, like data on a hard drive. Others propose that it's stored in the black hole's Hawking radiation, the faint glow of particles that black holes emit. But these ideas are still speculative, and the information paradox remains unresolved. The conflict between these two theories has sparked intense debate and research. Some physicists argue that our understanding of black holes is incomplete, and that a theory of quantum gravity, which merges general relativity and quantum mechanics, will resolve the paradox. Others suggest that the paradox is a sign that one or both of these theories needs to be revised. Despite the uncertainty, the information paradox has driven significant progress in theoretical physics. It has led to new insights into the nature of black holes, the behavior of information, and the fundamental laws of the universe. And as our understanding of these cosmic sponges continues to evolve, so too will our understanding of the information they hold. The holographic bound, a limit to knowledge. Black holes, those enigmatic cosmic entities, have long been a hotbed for scientific debate. At the heart of this intrigue lies the information paradox, a clash between two titans of physics: general relativity and quantum mechanics. General relativity, Einstein's brainchild, suggests that anything crossing a black hole's event horizon is doomed to an inescapable fate, its information lost forever. Meanwhile, quantum mechanics, the rulebook for the very small, insists that information can never be truly destroyed. This conflict has left physicists scratching their heads, searching for a unifying explanation. Enter the holographic bound, a mind-bending concept that proposes a fundamental limit to the information a region of space can hold. Picture a black hole's event horizon as a vast, two-dimensional surface. According to the holographic principle, the information within the three-dimensional volume of the black hole can be encoded on this 2D surface, much like a hologram. This idea stems from string theory, a framework that attempts to reconcile quantum mechanics and general relativity. The holographic bound suggests that the maximum information a region can contain is proportional to its surface area, not its volume. It's a radical departure from classical physics, where information scales with volume. This bound has profound implications for the information paradox. If the holographic principle holds, then the information swallowed by a black hole isn't lost, but rather encoded on its event horizon. This encoding, however, is far from straightforward. The information is scrambled and compressed, making it nearly impossible to retrieve. Think of it as burning a book and trying to reconstruct the story from the ashes. The words are still there, but they're no longer in any meaningful order. This interpretation aligns with quantum mechanics' no-cloning theorem, which states that information can't be copied, only moved or destroyed. Yet, it also challenges our understanding of general relativity, as the information isn't truly destroyed but rather transformed. The holographic bound also raises questions about the nature of reality itself. If our universe is indeed a hologram, then the three-dimensional world we perceive might be a projection of information encoded on a distant, two-dimensional surface. This idea, while counterintuitive, has gained traction in the physics community. Experiments, like the GEO 600 gravitational wave detector in Germany, have even hinted at a pixelated structure to space-time, a potential sign of this underlying holographic encoding. However, these findings are far from conclusive. The holographic bound remains a topic of ongoing research, a testament to the enduring mystery of black holes and the information they hold. The information paradox and the arrow of time. The information paradox and the arrow of time delves into the perplexing intersection of two fundamental theories in physics, general relativity and quantum mechanics. At the heart of this paradox lies the fate of information that falls into a black hole. According to general relativity, black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. When matter is consumed by a black hole, it seems to erase all information about its initial state. This poses a problem for quantum mechanics, which asserts that information is always conserved. The paradox intensifies when considering the arrow of time, the one-way direction in which time flows, as it challenges our understanding of causality and the nature of information itself. General relativity suggests that the information about the initial state of matter is lost forever once it crosses the event horizon of a black hole. This idea is often referred to as the no-hair theorem, which states that a black hole can be completely described by only three parameters: mass, charge, and angular momentum. Any other information about the matter that formed the black hole is seemingly irretrievable. This loss of information appears to violate the principles of quantum mechanics, which demand that information be conserved and reversible. The tension between these two theories has sparked intense debate and speculation among physicists. The arrow of time adds another layer of complexity to the information paradox. In classical physics, the laws of motion are time-symmetric, meaning they work equally well in both forward and backward directions. However, the arrow of time, as observed in everyday life, points in a specific direction from past to future. This directionality is closely tied to the concept of entropy, which measures the degree of disorder in a system. Entropy tends to increase over time, driving the arrow of time forward. In the context of black holes, the loss of information could be seen as a decrease in entropy, which seems to contradict the second law of thermodynamics. This apparent contradiction has led to various theories and hypotheses, such as the idea of black hole radiation proposed by Stephen Hawking, which suggests that black holes can emit radiation and eventually evaporate, potentially releasing the trapped information. One of the most intriguing aspects of the information paradox is the role of quantum entanglement. Entanglement is a phenomenon where two or more particles become linked, and the state of one particle instantly influences the state of the other, no matter the distance between them. Some physicists propose that information falling into a black hole might be encoded in the entangled states of particles near the event horizon. This idea, known as the black hole complementarity principle, suggests that the information is not lost, but is instead duplicated and transmitted to the outside world through Hawking radiation. However, this raises its own set of questions and challenges, particularly regarding the principles of quantum mechanics and the no-cloning theorem, which states that it is impossible to create an identical copy of an arbitrary, unknown quantum state. The interplay between these concepts continues to fuel ongoing research and theoretical exploration in the field of physics. The black hole information paradox, a philosophical conundrum. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and study. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. This is due to their immense density and the event horizon, a boundary beyond which all paths lead inward. But what happens to the information of the matter that falls into a black hole? This is where things get interesting, and a bit confusing. General relativity, Einstein's theory of gravity, suggests that the information about the physical state of objects is destroyed when they cross the event horizon. This is because the black hole's singularity, the point of infinite density at its center, is thought to obliterate all information about the matter that forms it. This idea is often referred to as the no-hair theorem, which states that a black hole has only three independent physical properties: mass, charge, and angular momentum. Everything else, all the intricate details and complexities, are lost. This seems to violate a fundamental principle of quantum mechanics, which states that information can never be truly destroyed. It's a bit like burning a book. The ashes might not contain the original words, but the information is still there in the arrangement of the atoms. Or is it? Quantum mechanics, on the other hand, posits that information is always conserved. This is a cornerstone of the theory known as unitarity. If information is lost in a black hole, it would mean that the universe is not following the rules of quantum mechanics. This is a problem because quantum mechanics has been incredibly successful in describing the behavior of the universe at small scales. So what's really happening? Is information lost, or is it somehow preserved? This is the heart of the black hole information paradox. The paradox has led to a lot of debate and speculation. Some physicists, like Stephen Hawking, have argued that black holes might eventually radiate away all their mass and energy, a process known as Hawking radiation. This radiation might carry away the information, but it's not clear how. Others have suggested that the information is somehow encoded in the radiation, but the details are still unclear. Still, others have proposed more radical ideas, like the holographic principle, which suggests that all the information in a volume of space can be encoded on the boundary of that space. This would mean that the information isn't lost, but it's stored in a different way. It's a bit like saying that a 3D movie is actually a 2D projection, but our brains interpret it as 3D. The paradox remains unsolved, a testament to the deep and mysterious nature of black holes. The future of information in black holes. Black holes, those enigmatic cosmic entities, have long been a subject of fascination and study. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. This is due to their immense density and the event horizon, a boundary beyond which all paths lead inward. But what happens to information that ventures too close? This is where things get interesting and a bit paradoxical. General relativity, Einstein's masterpiece, suggests that information falling into a black hole is lost forever. It's like burning a book. The information within is seemingly gone. This idea is known as the no-hair theorem, which states that a black hole has only three properties: mass, charge, and angular momentum. Everything else, including information, is lost. This leads to a problem when we consider the laws of quantum mechanics. Quantum mechanics insists that information can never be truly destroyed. It's a fundamental principle, a cornerstone of the theory. So, we have a clash. General relativity says information can be lost. Quantum mechanics says it can't. This is the information paradox. The future of information in black holes is, therefore, a hotly debated topic. Some physicists propose that information might be encoded on the event horizon, a concept known as holographic principle. Others suggest that black holes might eventually evaporate, releasing the information they've swallowed. This is known as Hawking radiation, a theoretical process where black holes emit subatomic particles. It's a slow process, but given enough time, even the most massive black holes could evaporate completely. Yet, this raises another question. If information is released, is it in a form that's usable, or is it scrambled beyond recognition? The answers remain elusive. Another intriguing idea is that information might be preserved in a higher dimensional space. Some theories, like string theory, suggest that our universe has more dimensions than the familiar three of space and one of time. In these extra dimensions, information could be safely stored, waiting to be retrieved. It's a fascinating concept, but it's also highly speculative. The truth is, we don't yet have the tools or the understanding to definitively say what happens to information in black holes. It's a mystery that continues to challenge and inspire physicists. The journey to unravel this paradox is far from over, and each new discovery brings us one step closer to understanding the true nature of black holes and the information they hold. So there you have it, the information paradox in all its mind-bending glory. On one hand, general relativity tells us that information can vanish into a black hole, never to be seen again. But quantum mechanics insists that information can't just disappear, it's got to go somewhere. It's like trying to decide whether your favorite pizza toppings should be pineapple or anchovies. Both sides have their arguments, but we're still waiting for that definitive consensus. Now, first know what you're thinking. This is all well and good, but what does it mean for me? Well, imagine a world where the very fabric of reality is a bit more unpredictable, where the rules of the universe are still being written. That's the world we live in, and it's pretty exciting if you ask me. The information paradox isn't just some abstract idea. It's a window into the deepest mysteries of the cosmos, and it's a reminder that there's still so much we don't understand. So what can you do about it? Well, for starters, you can keep asking questions. The next time you look up at the night sky, wonder about the black holes out there and the secrets they might be hiding. And if you're feeling really adventurous, dive into the world of physics. There are countless resources out there to help you explore these ideas further. And hey, if you're hungry for more mind-bending science, don't forget to subscribe to our channel. We've got plenty of other mysteries to unpack, from the quantum weirdness of the very small to the cosmic wonders of the very large. The universe is a strange and wonderful place, and we're just getting started. So, until next time, keep questioning, keep exploring, and who knows, maybe one day, you'll be the one to solve the information paradox. Thanks for watching, and see you in the next video.